Integrated Rate Laws, lecture number 17. So in the last time we talked about writing these overall rate laws by looking at experimental data where we looked at changing one concentration of reactant at a time and seeing its effect on the overall rate. We can actually look at a single reactant as time and make some other predictions. So we're going to integrate these rate laws over time, and it's going to give us these sort of integrated rate laws, right, which is going to allow us a second way to determine reaction orders by graphically, essentially. So an integrated rate law includes time as a variable. So now we're not talking about, we're including at some unit time in this rate law. So we're taking the rate and adding time to it. And we're going to look primarily at three different rate laws here: the zero order, the first order, and the second order. So in first order, we have rate is equal to a negative concentration change of A per time divided by T, which is going to give us a rate law of K times the concentration of A raised to the first power. If we look at that at time, over time, that's going to give us an integrated rate law of the natural log of the initial concentration of A divided by the concentration of A at any time t is equal to the rate constant times the time. If we do something similar for second and first or zero order, we see that we get these integrated rate laws. So the second order rate equation is going to give us 1 over the concentration of A at any time t minus 1 over the concentration of A initially is equal to KT. And for zero order, the concentration of A at any time minus the initial concentration is equal to the rate constant, a negative rate constant times T. So these are our integrated rate laws, and what they essentially allow us to do is if we graph our data using these forms, the sort of the line, straight line equation, if we get a straight line, that's going to be that order. So if we look at the first order first, we have the integrated rate law here. The straight line form, we're just going to move over that initial concentration. So it's going to be, if we graph the natural log of our concentrations equals a negative, or versus time, we would see that the slope of this line is going to be a negative k, and the y-intercept is going to be the natural log of our initial concentration. So if we graph the natural log of our concentration versus time and get a straight line, we see that that means that is first order with respect to that reaction. Or we can rate, if we know it's first order, we can relate its concentration at any given time versus using this straight line equation. Right? And this is going to give us a property, these integrated rate laws are going to give us a property we've referred to as half-life. Half-life is the time required for the concentration of the reactant to decrease by half of its initial concentration. Right? So if we look at the first order reaction where A naught over A t is equal A naught, or A, at time t is equal to 1/2 of its original, then this will simplify into the natural log of 2 over k. Right? So the half-life for a first order reaction is going to be equal to the natural log of 2, or 0.693, divided by the rate constant k, whatever value it is. Right? So we can then, if it's a first order, we can then calculate the rate life, or half-life. We will see later, or if you think of all those half-lives of nuclear reactions or radioactive materials, all of those sort of decays are first order reactions. So that's why we can talk about the half-life of something like uranium-235, right? Because it's following this first order kinetics, we can predict how long it's going to take before half of it whatever concentration we have, goes away. We can do something similar for a second order reaction. Now, notice we're going to graph 1 over the concentration versus time. Again, now if we get a straight line, we'll see a positive slope of k, and our y-intercept again is going to be 1 over the concentration initially. We can do something similar for the zero order. Now we're graphing one versus, or the concentration, just the concentration versus time. If we get a straight line, again it's going to be a negative slope, which is going to be a negative k, which means that this is going to be first order with a slope of a negative k. And our y-intercept again is the initial concentration. So if we look at here, this is the summary slide where we're talking zero order, first order, second order. The rate laws for those is, the rate law for a zero order is going to be the rate is equal to the rate constant k times the concentration raised to the 0, which is 1, which is why I'm not showing one there. We talked about the units before. The half-life now, you see, is going to depend on the amount we have initially for this zero order reaction. The straight line will form a straight line if we graph the concentration versus time with a slope of a negative k. For a first order, that's going to be rate is equal to k, the rate constant k times the concentration of that species raised to the first power. Now we saw the half-life is the natural log of 2 over that rate constant. And we'd get a straight line for a first order reaction if we graphed the natural log of the concentration versus time, again getting a negative, or slope with a equal to a negative rate constant k. Second order, rate is equal to the rate constant k times a squared, or to the 2. Now our half-life is going to be 1 over our rate constant times this initial concentration. And to get a straight line, we're going to graph 1 over the concentration versus time. So if we graph these, and you're going to do something very similar to this in lab, take some data, monitor it over time, and look at graphing one of these three ways to determine the order with respect to that single unit. Right, so that's one of the major things we want to get out of this is that we can relate by looking at the changing concentration with time. We can predict its order graphically. Right? If we look at the half-lives, the half-life of a zero order and a second order always depend on the initial amount present. Right? So I don't really like talking about half-lives in that way because it's going to change depending on how much we start with. For a first order reaction though, that initial amount doesn't matter. We always have a half-life is equal to the natural log of 2 over k. Right? But we can determine any of those half-lives, if you will, because of what they are mathematically equal to. It's the time it takes for the concentration to go down by 1/2, or a at some time is equal to 1/2 of what it originally is. But these also, depending on the order, will allow us to calculate concentrations at any given time of our reaction. Or if we know the reaction and how long it runs, we should be able to predict how much of that reactant is remaining. Right? So either way, this is a fairly useful measure, but it's primarily used for the zero, first, or second order reactions.